Okay, today we're going to begin our investigation into acceleration. And we're going to start this unit very similar to the way we started our last unit, is that we're going to look at some graphing. So what we've got here in this first graph is a position graph with an object that has an increasing speed. Now, there's a couple things that you need to notice when you're looking at the position graph and you see increasing speed. First of all, how do we know it's increasing? And how do we know it's changing at all? So when I look at this graph, I can tell that, very different to what we saw before, that the line is curved. So this line right here is curved. Now remember, for a position graph, what we saw before, we saw a lot of straight lines for position graphs. If we see a straight line, we know that the slope is constant. And we know that the velocity is equal to the slope. So as the slope is constant, then the velocity must also be constant. When I look at this curved line, I can see that the slope starts really shallow down here. And up here, it gets really steep. So therefore, I know when I go from a shallow to a steep slope, I know I'm going from a small velocity to a large velocity, so that means we have an increasing speed. We'll talk about decreasing in a little bit, okay? The other thing we can notice about this graph is in our previous experiments, we always used linear or proportional lines of best fit. You can see here that we used a quadratic fit. A quadratic fit is what we're going to use a lot of times when we have a curved line and we have an object with constant acceleration. So let's go ahead and talk about what acceleration really is. Acceleration, we're going to define it better, but I just kind of want to give it in some layman terms. Acceleration is a measure of the change in velocity. A better way to put this is that acceleration, and we use lowercase a to stand for acceleration. Acceleration is the rate of change of velocity with respect to time. WRT is with respect to time. So we can define that acceleration as the change in velocity over the change in time. Oftentimes, I'll drop that delta t, but we'll leave it in there for now. Recall that velocity is a change in position over a change in time. So they are very different, okay? Now, one of the other things we should remember is that if acceleration is equal to 0, it means there is no rate of change of velocity. The velocity is not changing. So when acceleration equal to 0, velocity is not changing, and that means then that the velocity is constant. So in our graph here, we see this blue line that I drew in has a constant velocity. This red line has an increasing velocity. We know that because the slope is changing on the position graph. So now we can go ahead and we can look at a velocity graph. Got a velocity graph here, and let's see what that looks like. Now, this is pretty different than what we've seen in the past. In the past, what we've seen for velocity graphs is always a horizontal line. That horizontal line has a slope that's equal to 0. Well, what we're going to see in a second here is that the slope of a velocity graph is equal to the acceleration. So if the slope is 0 on a velocity graph, the acceleration is 0. Here we can see that the slope definitely is not 0. Therefore, the acceleration is not 0. And even though the acceleration is not 0, it's still constant because the slope is constant number. means the acceleration is constant. That means we are gaining the same amount of speed with every equal time interval. And here we can see, because the values are increasing, right? Maybe the value of velocity here is, I don't know, 0.06, and here it's 0.3-ish. We can see that this has an increasing velocity. So let's take a look at, and let's go ahead and fill this out. What does the slope of the velocity time graph represent? We know that it represents acceleration. And we can look at our units. So we see that velocity is measured in meters per second, and time is measured in seconds. So let's go ahead and take a look. We can also see that the acceleration here is given by the slope, right? If the acceleration is given by the slope, we can tell that the acceleration for this particular graph is going to be 0.1688. So here we can say the acceleration is 0.1688. But we need some units here. And since this is a slope, we know the units are just the rise over the run. And I've asked you not to use this slash, but I'm going to use it for just a second, okay? So the rise units are meters over second. The run is in seconds. Well, that just looks awful. So let's see if we can simplify that a little bit. That's the same as writing 0.1688 meters per second divided by seconds. And to simplify that, you might remember keep, change, flip when you're dividing fractions in math class. So what that means is you keep the first part of the problem, so 0.1688 meters per second. You change the divide to a multiply, and you flip the last part. You make the reciprocal. So the reciprocal of seconds is just 1 over seconds, just like the reciprocal of 2 is 1 over 2. So now we can simplify these units. We see these seconds on the bottom are multiplied by more seconds on the bottom, so those aren't going to cancel. Those are going to become squared. So we get 0.1688 meters per second squared. And meters per second squared is going to be our standard units for acceleration. We're going to see those a lot. So we can fill in this next question. What is acceleration? Acceleration is just equal to a change in velocity over a change in time. And we're going to use our units of meters per second squared. I can write that a little bit better. And I can go ahead and make that like that. So what will that look like physically? So first, let's recall a little bit about constant velocity. And let's take a situation where our initial velocity is 2 meters per second and our acceleration is 0. Well, if our initial velocity is 2 meters per second, that means our final velocity and every velocity in between has to be 2 meters per second. We're not getting any faster, we're not getting any slower. We're always traveling at 2 meters per second. And let's just pretend we have a ball or something here. Here's the ball, right? And let's look at what's happening at several different times. We're going to take time 0, time 1 second, time 2 seconds, time 3 seconds, and times 4 seconds. Now, remember, at time 0, the ball is actually traveling at 2 meters per second. It's not stopped. And I know that because, remember, I can start my stopwatch whenever I want. So I'm going to wait for the ball to get up to its constant velocity of 2 meters per second, just like we did with the buggy in our constant velocity lab. And I'm going to say, well, the velocity at time 0 is 2 meters per second. That means 1 second later, it's still 2 meters per second. And 2 seconds later, it's still 2 meters per second. So the velocity is always going to be the same. So let's see if we can figure out how far the ball is going to travel then. If it's going 2 meters per second, that means that between time 0 and time 1 second, the ball has traveled 2 meters. And between 1 and 2 seconds, it's traveled another 2 meters. And between 2 and 3 seconds, another 2 meters. So you're seeing the pattern here, right? So the ball keeps traveling at 2 meters over and over and over again per second. And let's look and see what that means for our total distance traveled, because just like we did with our constant velocity labs, we're going to look at cumulative distance. So we can see that the cumulative distance over the first second is 2 meters, and then over the second, we've got 4 meters. And then 6 seconds is just 6 meters. And then 4 seconds is just 8 meters. So we went 2, we went 4, we went 6, we went 8 meters. We had a constant step size with each passing second. That's pretty much what we're familiar with. That's what we've been looking at so far. Now let's go ahead and let's take a look and see how this changes when we're looking at a constant acceleration situation. So in this case, we're going to start off with an initial velocity of 0. We're not going to let the object reach any kind of a cruising speed. But we are going to give a value for the acceleration. It's no longer 0. It's 3 meters per second per second. And I wrote it this way on purpose. I wrote it that way because I want to make sure we understand what's actually happening here. So let's take a look and let's label a couple things. And I'm going to cheat a little bit because I'm going to put 1 second. Oh, I don't like how I did that. I'm going to put 1 second. Okay. So this is time 0. I'm going to put time 0 right there. And I'm going to have time 1 second later. And I'm going to try and put in some values for velocity. I know that right here we said that the initial velocity is 0. Well, what's the velocity at time 1 second? That's where knowing my acceleration is going to help, because what this is telling me is that the object is gaining 3 meters per second of velocity every 1 second. So the velocity at time 1 second is actually going to be 3 meters per second. Now the question is, well, how far did the object travel? And this is where it gets a little tougher. And I can use an idea of average velocity, okay? And I can write average velocity in one of two ways. I can write V average, which is the same as V with a little bar over it. And I can calculate the average velocity just the way you calculate average velocity in math class by adding up the two numbers and dividing by 2. So I can see for this first step, the initial velocity was 0, the final was 3. So 0 plus 3 is 3 divided by 2. You probably don't even need a calculator. The average velocity was 1.5 meters per second. And because that's the average over the total time, that's 0 to 1 seconds, I can then figure out the delta x for that time period in 1 second, and I know the object traveled 1.5 meters in that first second. So I can go ahead and put this was 1.5 meters. That's a lot, and we're gonna keep going. We're gonna do another one, okay? So now let's look and see what happens between 1 second and 2 seconds. And I'm gonna cheat a little bit because I know my step size is going to get bigger. So after 2 seconds, I know that the velocity is now different than 3 meters per second. It's changed. 1 second has passed, so the object has gained another 3 meters per second of velocity. It's now traveling at 6 meters per second. So it's gone quite a bit faster. Now the average velocity during this time from 1 second to 2 seconds, let's see, 3 plus 6 is 9 divided by 2. The average velocity for that time period was 4.5 meters per second. That means between 1 second and 2 seconds, the object traveled 4.5 meters. We figured that out just the way we did before. Then we can look at 3 seconds and say, well, what's the velocity at 3 seconds? And that's an instantaneous velocity. It's only valid at 3 seconds. Not at 3.1 seconds, not at 2.9 seconds, right at 3 seconds. Well, another second has passed, so we've gained another 3 meters per second of velocity. The object is now traveling at 9 meters per second. Well, what's the average velocity between 2 and 3 seconds? The average velocity, let's see, 6 plus 9 is 15 divided by 2. The average velocity is 7.5 meters per second. And since it's an average, that's valid between 2 seconds and 3 seconds, the entire time. That's the average velocity for that time period. That means the object traveled 7.5 meters in that amount of time. And finally, if we want to go one more, we can go all the way to 4 seconds. Maybe it's somewhere out here. Okay. We can see that again, we've gained 3 meters per second of velocity. So 3 plus 9 is 12 meters per second. Okay. I can see that the average of those two, let's see, 9 plus 12 is 21 divided by 2. So the average velocity is going to be 10.5 meters per second. So in this case, the object has traveled 10.5 meters per second. So you can see right away that there's a huge difference between what happened in a constant velocity situation and what happened in a constant acceleration situation. Here, with constant velocity, we had equal step sizes. Here, our step sizes kept getting bigger and bigger and bigger. So a very different outcome and a very different feel for what we would have compared to a constant velocity situation. Let's talk about one more thing before we end our notes here. Okay, let's talk about the direction of acceleration. So much like velocity, acceleration can be positive or negative. Okay? So all that means, and a lot of people kind of make a little bit of a mistake here. They kind of say, well, if it's positive, the object must be getting faster. If the acceleration is negative, it must be getting slower. And that's not true. And we're going to talk about this quite a bit. But let's take the easy example first. And let's say we have an object that's moving in a positive direction. Well, if it's moving in a positive direction, it must have a positive velocity. And let's also assume that we have a positive acceleration, just like we did in the example above. Well, in this case, I would agree. This object is getting faster. And I always like to think of acceleration as if a string were attached to an object. If the string were attached to an object, which way would it be pulling? That's how I figure out the direction of acceleration. So in this case, there must have been a string, and it must have been pulling the object in the direction of forward positive velocity, and therefore the acceleration was also positive, and we know that object was getting faster. Now let's take a look at another situation where we have positive velocity but negative acceleration. In this case, the object is moving in a positive direction, but the string is pulling it backwards. I think you can see why, in this case, the object would certainly be getting slower. Now let's switch it up a little bit. Let's say we have an object going in a negative direction and a positive acceleration. So it's moving along in the negative direction, but something is pulling it back towards the positive. I think you would see in this case, again, the object would be getting slower. In our last situation here, we'd have negative velocity and negative acceleration. So the object is moving in a negative direction. Something is pulling it in a negative direction, so it has a negative acceleration. Well, I think you would see in that case, again, it's getting faster. So a couple things you can notice here. The first thing I would notice is that when positive velocity, positive acceleration, getting faster. Negative velocity, negative acceleration, getting faster. So when the signs are the same, right, positive and positive or negative and negative, we have a situation where the object is getting faster. When the signs are opposite, so negative and positive or positive and negative, in this situation, we have an object that's getting slower. All right, that's all we have for our intro to acceleration. We'll have lots of practice on kind of how to set some problems up and how we're going to use this as we go through the next couple of days. Have a great day.